This is chemistry 1412, general chemistry 2. The context of the course, or the main theme of this course, is the study of chemical reactions, or how to study chemical reactions. As you grew up through a chemistry course, you were introduced to chemistry in terms of material world. Chemistry is study of matter. Anything that has weight occupies space. So that leaves us with a wide open world of everything. In order to learn the concepts and the particular specifics in a chemistry course, we need to break it down to something that is simpler and easier to digest as we study. And it was found that it's by following what we call John Dalton's postulates on theory of matter, we found a method for systematically covering the material that's easier for students like you to digest. And this evolved from very basic particles to the more complex, is the idea. Now, when Dalton wrote his postulates, he had no idea of the microstructure of the atom. He simply said that all matter consisted of particles, and he went from there and built the organization of the study of chemistry. But over years following that, we know the atomic theory has evolved to reveal the microfine structure of the atom down to the nuclear substructure. Well, the chemistry course that you have been taking and will take has followed this protocol. Fundamental particles, which we recognize as the protons, the neutrons, and the electrons. And we followed that with putting together the systematic organization of the atom. So this gives us the atom in itself. Now, an atom is one particle with a certain structure. Elements are a whole lot of atoms. So the difference actually between an atom and an element is just in numbers. Same way with molecule and compounds. So if that perception hasn't hit you yet, that's essentially the difference. They're really the same thing. Elements and atoms are the same thing. They just have structural differences, but they differ primarily in quantity. So we go from atoms to elements. And periodic table, organization of the periodic table, ions, cations, anions, and so forth, evolved from that study of elements. Then what happens when we put elements together? We form molecules. Molecules are entities that contain two or more elements and have very specific and unique properties within themselves. Then molecules is a specific structure. Compounds are a whole lot of molecules. We got to look at compounds in the context of large quantities, which defines, larger masses and moles and mechanisms by which we can weigh and detect and study larger quantities of molecules. And when molecules, compounds interact with themselves as well as or elements, we call them chemical reactions. So we have chemical reactions. A chemical reaction can only produce one of three things. Anybody want to try that? One of three. The only three. Solid, a liquid, or gas, right? Now there are a whole lot of solid structures, a whole lot of gas, a whole lot of liquid structures, but that's all it. Now, we don't talk about plasmas in general chemistry courses. That's temperatures above 5, 6, 7,000 degrees Celsius and things like that, where everything is in particle form. Everything's below 5,000 degrees in here, cool, essentially. So we call this states of matter. And learn about how they solids hold together and why they do, why liquids liquids, you know, this kind of stuff. This stuff that you possibly have covered or remember as you grew up in the subject matter. And solids, liquids, and gases can be mixed together and form a thing called solutions. Solutions, by definition, are homogeneous mixtures. Please remember that. Having consistent properties throughout. A solution is typically characterized by an amount of solute in a solvent, and the distribution of that is homogeneous. And we will do one of the initial things we will do in lab after our statistics, that won't take any time, is learn how solutions are treated, made, and evaluated. That is a critical. So many students come out of chem class, they can't do a simple solution. Okay, make a simple solution. Hopefully you will understand after we get through this. That completes Chem 1. As far as most courses go. Now, you have variations, but 99% of the college and high school chemistry courses that are presented in the United States anyway follow this protocol. Up to this point, you have completed Chem 1. Then you get into Chem 2, which is the study of chemical reactions. This is where you are now. This means that you have to be an expert. I expect you to, no, I don't think that's going to happen. Be an expert in all the materials up to this point, right? You're going to remember all the details. Sure. Okay. I'll fill in the blanks for you. Okay. Now, what you are going to be covering in the study of chemical reactions is three fields that define the nature and characteristics of chemical reactions. This includes chemical kinetics, chemical equilibrium, and chemical thermodynamics. An entire chapter deals with the study of chemical kinetics. About 6 or 7 chapters deal with equilibrium concepts. And then we have one very large chapter on thermodynamics. Actually, one of them is in Chem 1. If you recall, you may have covered Hess's law and energy changes in chemical reactions, but we'll treat them of that also in this course, as well as a new term that you may not have heard of called enthalpy. Entropy and enthalpy. Okay? Enthalpy is the heat of reaction. Entropy is the state of disorder, or state of disorder that a reaction changes to. Some reactions lose a quantity of disorder, and some reactions acquire a greater quantity of disorder. Now, we're used to thinking in terms of, well, it's getting more disordered and less disorder. You don't think in that term. You have to kind of think backwards when you start dealing with the thermodynamic issues. We'll get to it. But at any rate, what do each of these provide as you use them? And what should you use them for? Chemical kinetics tells us about the rates of chemical reactions, how fast a reaction proceeds from reactants to products. And we look at things that are called rate laws. And those rate laws are mathematical reflections of what the chemical reaction can do. And we will learn, or you will be exposed to those anyway. Chemical equilibrium deals with the extent of reaction. From inception, that is when A and B come together, to a point at which the concentrations of products and reactants do not seem to change, is called an extent of reaction. And from that point where they do not appear to change, we call the equilibrium region. I'll show you this in just a second. But first, thermodynamics defines the feasibility of chemical reactions. Simple. Will it work? Will it not work? Thermodynamics is a relatively young science. It evolved from the need to study concepts dealing with steam engines back in the Industrial Revolution. And it's quite sophisticated, and it can get very difficult. But we're just going to look at the fundamentals of the first and second laws that evolve in here. All of these are connected together in any kind of chemical reaction that you work with. One evolves into the other in a very simple graphic. As a function of time and concentration, when we consider changing concentration, that should be change in concentration as a function of time, we are going to look at reactants going to products. At time equal 0, you have 100% reactants. The reaction hasn't started yet. I will use an analogy similar to horse racing, whereby the reactants are in the starting gate, and the starting gate has not opened yet. Very simple idea. Everybody gets that pretty quick. Then at your chosen point of issue, time, you open the gates and let the reaction run. The question is, what happens to the concentration of reactants as products are produced? Well, this can be shown generically as a decrease in reactant concentrations. I'm just going to put reactant concentration right here. At the same time, we have increasing, let's see if I get that done right here, make them at least look alike, product concentrations, like that. This is not a mystery to most of you. Now, what is a mystery, or may be a mystery, is that when you look at this relationship here, there's a point in here where the concentrations do not change. The concentration change, here the concentration is constantly changing, going up to that point. When we study chemical reactions. We divide our study into these two areas. When we study chemical kinetics, we'll be studying behavior of reactions in this first portion right here, in which the concentration slope is never zero. It continues to change toward the zero slope. At the zero slope point, you enter what we call the equilibrium region. This is the kinetic region. This is the equilibrium region. And the principles that we will study will define the behavior of reactions as they reach out toward that kinetic region, and the behavior of reactions beyond that point of where it reaches equilibrium.